All right, so we talked about this a little bit on the first day, but chemists usually make measurements on bulk samples, even though we are interpreting the results and thinking about matter on the molecular scale. So the connection between the atomic scale and the macro scale is a chemical counting unit called the mole, or mole without an E is the abbreviation. Makes it a lot shorter, of course. The mole relates the number of carbon atoms to the sample's mass using the conversion factor 6.022 times 10 to the 23rd atoms per 12 grams of carbon-12. So remember I mentioned briefly that carbon-12 was our standard and 12 grams of carbon-12 was how we came up with atomic mass units. So this is why, because this is our relationship to the macro scale using Avogadro's number, which is 6.022 times 10 to the 23rd. So it was named after the scientist who first proposed that equal volumes of different gases at the same temperature and pressure contain the same number of particles. You don't need to know that right now, but Avogadro is going to come up again in Chem 119. So keep your eye out for him. All right, so when they were determining the charge on a single electron and the charge on 1 mole of electrons, that yields the number of electrons in 1 mole of electrons. So 1 mole of electrons is this much, and we were able to determine that based on the charge of a single electron, which we determined in the Millikan oil drop experiment from chapter 2.2, and the charge, which was also determined there, and that got us to a mole of electrons. 1 mole of any element also contains that many atoms of the element. So a mole is just a counting unit. So you know how 12 is a dozen, like a dozen eggs? Or 2 is a pair? A mole is a really, really big number, to be fair, but it's still just a number of things. You can have a dozen donuts. If you baked for probably hundreds of years, you could have a mole of donuts. Maybe more than hundreds of years. It's a lot of donuts. Anyway, a mole of any element contains exactly 6.022 times 10 to the 23rd atoms of that element, always. That's what a mole is. And here we can see a mole of copper, a mole of aluminum, and a mole of sulfur. And they look like different amounts, but they have the same number of atoms. The key is that those atoms weigh more, some weigh more and some weigh less, and those atoms, some are bigger and some are smaller. So that's why they don't look the same, but they have the same number of atoms, I promise. All right, so we use Avogadro's number to convert between moles and the number of particles in a sample. So if we want to know how many moles of silver are in 2.40 times 10 to the 26 atoms of silver, we just use Avogadro's number. So I'm going to start with 2.40 times 10 to the 26 atoms. And I want to convert to moles. So I want to have moles on top, and I want to have atoms on the bottom. So 6.022 times 10 to the 23rd, 23rd atoms in a mole. Just like there could be 6.022 times 10 to the 23rd donuts in a mole of donuts. It's just a counting unit. So now we can cancel out atoms and we'll end up with moles. So you just plug that in your calculator, 2.40 times 10 to the 26 divided by 6.022 times 10 to the 23rd. And I got 399, almost 400 moles of silver, which is a lot of silver. All right, cool. Does that make sense to everybody? I hope so. You can go back to before I wrote on this slide and practice it yourself and see if you get 399 moles as well. All right, so molar mass. So let's keep going. There's something called molar mass or molecular weight, and that could be written as M. So sometimes there's like a cursive M in your textbook. Sometimes you'll see MM for molar mass or MW for molecular weight. They all mean the same thing. That is the mass in grams of 1 mole of atoms of that element. And I'm going to show you what that means here. So we talk about atoms in atomic mass units. So one carbon atom, one carbon-12 atom to be specific, is exactly 12 atomic mass units. 1 mole of carbon-12 atoms, so a whole lot of carbon-12 atoms, weighs exactly 12 grams. So the conversion comes from Avogadro's number, where we can talk about grams, which is a realistic weight, versus atomic mass units, which is not. So we're always going to talk about the molecular weight in the lab and not the atomic mass unit weight in the lab. So let's look at a different example. Magnesium has an atomic weight of 24.31 AMUs, atomic mass units, and 1 mole of magnesium atoms has a mass of 24.31 grams. It's always the same. It's based on the Avogadro's number. It's based on the number of things in a mole. All right, so now that we know about molar mass, we can convert between moles and mass in grams of a sample. So how many moles of zinc are in 163 grams of zinc? You can pause and practice this on your own. Okay, I'm going to do it. So we have 163 grams of zinc. And then to get our conversion factor, we have to actually look it up on the periodic table. So I looked up zinc on the periodic table and I found that zinc has an atomic mass of 65.38 AMUs. But if we're looking at a mole of zinc, it's going to be 65.38 grams. So that's what my conversion factor is going to be. 65.38 grams for 1 mole of zinc. All right, now we cancel out our grams and we're going to get our answer in moles, which is 2.49 moles of zinc. So you should be able to do this way or the opposite, find the mass of however many moles of zinc. So make sure you can do both. Same thing with atoms and moles. Make sure you can find the number of atoms based on a number of moles or the number of moles based on a number of atoms. Listen to this slowly and it might make more sense. I'm sorry. All right. So now that we have Avogadro's number and molar mass, we can relate mass, moles, and atoms of an element. So let's take a look. We've got 5.76 times 10 to the 22 chromium atoms. So that's what I'm starting with. So I'm going to write it over here. So that's atoms. And I want to find a mass. So first, I'm going to go to moles so that I can find the mass in grams and not atomic mass units, because grams are a realistic, practical mass that you can measure in the lab. Atomic mass units are not. So I'm going to convert to moles first. and you convert to moles using Avogadro's number. So that is 6.022 times 10 to the 23rd atoms in 1 mole. Okay, and now you have to look up the atomic mass of chromium atoms or of chromium on the periodic table. And that mass is 52.00 grams per mole. Because when I looked it up on the periodic table, I found that an atom of chromium is 52.00 atomic mass units. So I looked at the average atomic mass on the periodic table and then converted it to grams per mole so that we can use our practical measurement of mass in grams. All right, so we got atoms on top and bottom, atoms cancel out. We got moles on top and bottom, moles cancel out, and we're gonna end up with grams. So we just plug that in our calculator real quick. I'm gonna do it right now while you're doing it. And I got 4.97 grams is my answer. Cool. So that is definitely a mass you can measure on a balance in the lab. That's awesome. That is how much 5.76 times 10 to the 22nd chromium atoms weigh. Not that we could ever count 5.76 times 10 to the 22nd chromium atoms. Cool, huh? It's unit conversions, and now we're learning about moles and mass and putting it all together. It all adds up. And this is just a graphic. This is from your book. If you tend to like to do things in like flowcharts or have visuals of what you're doing, this is how you would do that. So you can go from grams to moles with this conversion. You can go from moles to grams with this conversion. You can go from moles to atoms with this conversion, and atoms to moles with this conversion. And if you need to go from atoms to grams like we just did, you need to use both. If you wanted to go from grams to atoms, which is the opposite of what we just did, you'd need to use both. Okay, cool. That's it for today. I'll see you guys in class tomorrow.